Well, heidi ho. Today we're going to continue with optimization problems, and the example we're going to start with is a little bit complicated, but I also think it's fascinating, and it is definitely a real world sort of a problem. So let's dig in. An oil refinery is located on the north bank of a straight river that is 2 kilometers wide. A pipeline is to be constructed from the refinery to storage tanks located on the south bank of the river, 6 kilometers east of the refinery. The cost of laying pipe is $400,000 per kilometer over land to a point P on the north bank, and then $800,000 per kilometer under the river to the tanks. To minimize the cost of the pipeline, where should P be located? All right, that is a lot going on. Let's draw a diagram so that we can start to see what's going on here. Okay, so we have our river. It is 2 kilometers long. So I'm going to draw this and say 2 kilometers long. And we know that so we've got the refinery, we can call that R, and we've got the storage tanks, we can call that S. And we know that the storage tanks are 6 kilometers east of the refinery. So this distance here is 6 kilometers in total. And we need to construct a pipeline from the refinery to the storage tanks. And there's different ways of doing this. We could just go diagonally straight across the river and just have it all be underwater. But the problem with that is that it's more expensive to make it underwater than it is over land. So maybe that's not the best option. We could try to minimize the distance under the water. So we could have it go all the way across and then straight down, or straight down and all the way across. That would minimize the amount of pipeline that's going under the water, which is more expensive, but it does feel like it's kind of a long distance. It might be that there is some point P somewhere in the middle that is X kilometers away from the point on the opposite bank of these storage tanks. And it might be that we then build the pipeline overland to P and then diagonally across to S, to the storage tanks. That would make a little right triangle for us. So it might be that there is some optimal point in between just doing it all directly underwater or kind of going all the way over here before crossing. And so we want to figure out what the best option is for this point where we go from the overland to underwater portion. So there are still a couple of things that we haven't labeled yet that are important. We need to know what this distance is. That's going to be how much length of pipeline is going over land. And if the whole distance is 6, but this bit is x, then this is the leftover bit, 6 minus whatever x is. And then we also need to know this diagonal, the hypotenuse of this right triangle, because that's going to be the length of the pipe that's going underwater. And we can use the Pythagorean theorem here. If the legs of this triangle are 2 and x, and we need to know that distance, then d squared equals x squared plus 2 squared. That's the same as x squared plus 4. And if we take the square root, that gives us the distance as the square root of x squared plus 4. So this is going to be the square root of x squared plus 4 based off of whatever we choose for x. So we need to minimize the cost of the pipeline. So we want to know the cost of the pipeline as a function of x, because it does depend on what this length is. Because if we choose a different point for P, that's going to change the distances and the costs. So we know that it's going to be $400,000 per kilometer over land. And the overland distance is 6 minus x. So that's going to be 6 minus x times, let's just say 4, let's measure this in terms of hundreds of thousands. So we're measuring this in hundreds of thousands of dollars. So we can say that that's 4. And then plus, it's going to be the distance of the portion that goes under the water, which is the square root of x squared plus 4, times the price per kilometer there, and that's going to be $800,000 per kilometer. So we're just going to say 8 because this is measured in hundreds of thousands of dollars. That is the unit of measurement here. Just makes it a little bit easier so we can work with smaller numbers. So this is the cost function. It is not nice, right? We've got a square root of a polynomial, but one nice thing is that it's already only in terms of one variable, x. So we don't have to go and use some sort of a restriction like we did in some of the other problems to eliminate one of the variables. We are just ready to differentiate at this point. So that's going to give us c prime of x equals, the derivative of 6 minus x is -1, and that's going to get multiplied by 4, because we don't have to use the product rule here. When it's just a numerical number, a numerical multiplier times a function, then the derivative is just the derivative of the function times that number. So that's going to be -4, because it was -1 on the inside times 4. And then plus 8 times, and we need to differentiate this radical. Now we know that the derivative of the square root of u is 1 over 2 root u. So it's going to be 1 over 2 root x squared plus 4. And then we have to multiply by the derivative of the inside, which is 2x. The derivative of x squared is 2x, and the derivative of 4 is nothing. So if we look and see if we can simplify anything, we do have those 2's canceling out, which is nice. So then this gives us -4 plus 8x over the square root of x squared plus 4. And we want to know when this equals 0, or when this is undefined, because that will give us our critical numbers. Now this is never undefined because that denominator is always positive, so we don't have any problems there. If we want to know when it equals 0, we've got some solving to do. We can add 4 to both sides. That gives us 8x over the square root of x squared plus 4 equals 4. And then we can multiply both sides by the denominator to get rid of that denominator. So that's going to give us 8x equals 4 times the square root of x squared plus 4. If we divide both sides by 4, that gives us 2x equals the square root of x squared plus 4. And if we want to solve that, we can square both sides. That'll give us 4x squared equals x squared plus 4. I think we're getting there. Subtracting x squared from both sides gives us 3x squared equals 4. Divide by 3, x squared equals 4/3. And if we take the square root of both sides, that's going to give us x equals 2 over root 3. We don't need to worry about -2 over root 3. Here's the thing. If we go back to our diagram, x has to be positive or 0. If x is negative, that means that p is somewhere over here. And of course, it's going to be more expensive for us to go fully out of the way and then have to loop back. That would be ridiculous. X can only be between 0 and 6, because we know this point is going to be somewhere between the refinery and the storage tanks. So 2 over root 3 is the only critical number. Now, we can actually use the closed interval method here because we know that x has to be between 0 and 6, and we've got a continuous function that is differentiable on its domain, So that means that any maximum values, any global maximum, is going to occur either at the critical number of 2 over root 3 or at one of the endpoints, and those endpoints come from x equals 0 and x equals 6. And so we need to look at the cost function for each of these values and see which one gives us the minimum cost. So I think c of 0 is probably going to be the easiest to calculate. I'm going to start there. If x is 0, then we've got 6 times 4 is 24. And here we've got 0 squared plus 4 is 4. The square root of 4 is 2, and 2 times 8 is 16. So we've got 24 plus 16, which is 40. And remember that this is in hundreds of thousands of dollars. So 40 times $100,000 is actually $4 million. So that is the cost if x is 0, which means the point where we cross the river is right across from these storage tanks. Let's see. If our value of x is 6, that means actually that's going to be the fully diagonal version, because that means that P is all the way over at the refinery. If we plug that into the cost function, 6 minus 6 is 0. So this first term goes away. And then here, 6 squared is 36 plus 4 is root 40 times 8. So that's 8 root 40, which if we plug into a calculator is about 50.6. So we're looking at $5,060,000. And then we can look at our critical number and plug that in. And I'll be honest, I'm just going to use a calculator to evaluate that. When I do, I get that this is approximately equal to 37.9, which would be approximately $3,790,000. That is the cheapest. We beat this other version by just over $200,000, which is nothing to sneeze at. That could be the annual salary of a few employees. And so this is going to be our optimal value of x. So we're asked, where should P be located? So it should be located 2 over root 3 kilometers west of the storage tanks. And that is approximately equal to 1.15 kilometers west of the tanks. So that would save us about $200,000 from the option if we just go all the way straight across and then cross the river right at the storage tanks.